This is video 3 for lesson 1, part 1 for electrochemistry and chemistry 2. We are going to be using a reference packet, and I included this in the Schoology site. If you are not able to print this out, then you'll just have to look up the values for things. So we are going to be using them, and my paper here is blue because I usually have a class set of these and they're blue. But you can see that we have an alphabetical listing, and we're only going to use table 1 from this packet. So you don't have to copy or print out the whole thing, just enough pages for table 1. But as you can see, we have these different equations here, and they look like half reactions, which they are. So this first one says Ag plus an electron is in equilibrium with Ag. And the value in volts is 0.7996 volts. So the way we're going to use these is we're going to look them up. And if we have to reverse the reaction, we're going to change the sign on this, just like we did back when we talked about Hess's law in thermochemistry. So these are all written as reductions. So if it's the oxidation equation, we need to flip the equation and we need to reverse the sign. So we're going to set this to the side, and we're going to talk about how we start solving these problems to calculate E prime for a cell. So the first thing we're going to do is we're going to write the given reaction as two half reactions. And we are going to balance the reaction, or the half reactions, for the number of electrons. So basically, we're going to find out what is the LCM. And we're really not going to use that in this problem or this worksheet, but we will in future worksheets. We're going to ID which reaction is the reduction, which one is the oxidation, the reducing agent, the oxidizing agent, the cathode, and the anode. So it's just a lot of ID. And then we are going to look up reduction potentials for each half reaction. So we're going to use our chart. Now, here, if the half reaction is oxidation, we reverse the sign of E prime from the chart. The other thing, these reduction potentials are intensive properties. And if you don't remember what that is, it doesn't matter about how much there is of the substance, it's the value. You could have 10 pounds of copper or silver, and you're going to get the same voltage out of it, no matter how much you have. So the moles of this does not matter. So that's what this little thing is here. Never multiply the E prime values from the chart based on the LCM. This is an intensive property. So our fifth step is we just add the two half reaction E prime values. And our last thing we're going to do is we're going to learn something called line notation. And this is just a shorthand that chemists used to tell what is the makeup of a galvanic cell. So we write the anode first and the cathode second. Like a parallel symbol separates the electrodes, and a single line separates the parts of the two half reactions. So if we use the example that we had from our diagram in video 2, where this was our equation, so I just copied that equation again. We identified the zinc half reaction, zinc solid to zinc plus 2, as the anode. So I would write zinc solid, a single line, because it separates the parts of the half reaction, zinc plus 2 AQ. So that's the anode. I'm going to put a double line to signify that that is the anode. And now we're going to have the cathode, which is copper plus 2 AQ, single line, copper solid. So the last thing we're going to do is look at an example, and I'm going to zoom in here a little bit. Here is our equation. So I'm going to write this as two half reactions. So I'm going to have Fe plus 3AQ yields Fe solid. And I'm going to have copper solid yields copper plus 2Q. So now I'm going to balance it for electrons. So our first one, we have to have 3 electrons on the left, and this one we have to have 2 on the right. Our LCM would be 6. And that's really all we're going to do with this. In our next part of lesson 1, we're going to talk about, and we're going to actually use that LCM. And now I'm going to look up the values for these two. And we can already go through and write down, okay, well, this is gaining 2 electrons, so this is reduction, which means it's the oxidizing agent, and it's the cathode. Once you have one, the other one has to be the opposite, so this is oxidation, because we are losing electrons, so this is the reducing agent, and this is the anode. And we can look up our values. So in our chart, they go in alphabetical order, so I'll look up copper first. And this is probably the hardest part of all of these, is finding these. So if we look up copper, copper is up here, and we have a lot of different choices here, but we have to make sure that we have the one that has copper plus 2 going to copper solid, or copper solid going to plus 2. So if we look at this one, it's right here. And we see that it's reversed from this. So this value we have to make negative. So this is going to be negative 0.3419 volts. So this is the one that was reversed. You don't have to write reversed, but because it's written the other way in the problem or in the chart, we have to reverse the sign so it matches what we have. And then we have to look up iron. And iron is right down from there, but we have to make sure that we have the correct one. So we are going to be using this one right here, the middle one, and it's negative 0.037, and it's written like we have it, so negative 0.037 volts. All I'm going to do is add these two together. So I get the E prime for the cell equal to negative 0.379 volts. And the last thing that I'll do is write the line notation. So we write the anode first, which is the copper. So copper solid, the copper plus 2 AQ. Double line to separate the anode and cathode. I got Fe plus 3 AQ. Single line, Fe solid. So there are our two answers plus our labels over here. So you should have everything you need to complete our first worksheet, which is standard reduction potential worksheet.